Welcome to Empowered Learning. This video will be about solving linear first-order equations. We'll first talk about the basic notation or form of a first-order linear ODE so that when you see a first-order linear equation, you'll be able to recognize it. The second thing that we'll do is go through the whole procedure of how we actually derive this process of solving linear first-order equations. And that will culminate in either a process and or formula that we could use to be able to solve these types of equations. I will be going over both methods during this video, so you'll see some examples to where I will do it the more traditional way. You'll see other examples where I just used the formulaic way of being able to solve these. Regardless of which way I solve these examples, the one thing that ties them both together is this concept called the integrating factor. And we're going to learn about the integrating factor for an ordinary differential equation and how that plays a role in having us to be able to simply solve this type of equation. Next, we'll do an abbreviated summary of solving these first order linear ODEs. And that's just me simply saying, hey, if you want to do this the traditional / systematic way, you could do it like this. If you want to do it the formulaic way, you can do it like this. Okay. And then, of course, we'll go through some examples. All right. So what is a linear first order ordinary differential equation, or ODE as I like to call it? It is a first order ODE of this form. And of course, you see it in two different forms, but they're literally the same thing. Some people like to write it in this form here where they just have dy over dx, and that equals to some function minus another function times y. My preferred way of looking at it is like this, where we have dy over dx plus some function times y plus, equals another function. And so I prefer this way because this looks like first derivative, no derivative, but just the regular function, and then equals, and this doesn't have anything by our function r of x. And so you'll see that for most of the examples that I do, I stick with this second form here, just because I think it's a little bit more easy to recognize. But if you like this form, you could also do it this way. Everything that I'll do will still work with it being this way. The only thing that may change is the fact that you'll have to switch your signs. So I guess the formula or the process that I use in this form, you'll have to change the sign on p of x to be able to make that happen. Now, p of x and r of x will be known functions. So when we have our differential equation, you will know what p of x and r of x are. Your job will be just to recognize it, okay? And they are functions of only x, or they could be constant values. So we could have something like r of x could be 2x squared, or it could be something like -3, okay? Now, note we will rearrange an ODE that is classified as a linear first order in standard form, as it will be easier for us to recognize and use it in this form. And so that's just me basically saying I prefer to use the second method here. Now, we will investigate how we actually solve equations like these. And note that we are purposely going to use the long way of solving this type of equation so that you'll gain the intuition of knowing the twists, turns, and tricks involved in solving these equations here. And so again, the purpose of this is just to give you some kind of background knowledge of saying, hey, now that I know what this process is actually doing, you can choose for yourself by having the intuition of knowing what it's all about, whether you want to do more the traditional systematic way of solving these types of equations, or if you want to use the formula way. Okay. All right. So let's go through this actual procedure. Okay. Now, the procedure that follows will take you through the derivation process to see how we solve linear first order ODEs. Although the end result will be a nice, concise formula that we can use to solve these, types of equations quickly. It is important to actually go through this process at least once, as by doing it, we will gain the intuition that will, number one, help us to know when we actually need to use the resulting formula we will come up with, versus figuring out the key thing we need by inspection. And two, help us to understand the motivation for other ordinary differential equation solving techniques for other types of ODEs whose foundation is rooted in the procedure we will learn here. Okay, so basically, I know that was a lot, but basically all I'm saying there is, number one, we have a choice on solving the equation by basically formulaic way, or we can do it the traditional way. And in some instances, we can actually look at our equation and see by inspection what that integrating factor actually is. Okay. Now, I don't go into detail with that here with the examples that I give here. I kind of keep it more systematic. But of course, if you work with these over time, you'll start to see, hey, you know what, if my integrating factor was just this and I applied it to my equation, then everything would work out. But you have to be kind of well versed in doing these kind of equations for a while. And so since we're first learning them here, I'm not going to try to get you to see that at this point. Okay. All right. So the other thing is that some of the other techniques that we are going to be focused on are going to come from this process of solving first order linear ODEs. Okay. And as I say here, two such examples of other equation types that will have its foundation in the process that we're going to study here are going to be Bernoulli equations and first order homogeneous or homogeneous equations. And so I have a video on each of these types of equations. So if this is sort of the next step for you after you learn how to solve first order linear equations, then you may want to look at the videos for Bernoulli and homogeneous equations as well, or first order homogeneous equations. All right, so the goal of our derivation here. So what we want to do is we want to transform a linear first order ordinary differential equation. In other words, an equation that looks something like this. We want to transform that into an ODE that is just a function of x on both sides. Okay. Now, what does that basically mean? It just means that we want our first order linear ODE to turn into a directly integrable ODE. Okay. And sometimes it may end up looking separable as well. So in a nutshell, the basic idea is a first order linear ODE is, I'll say, an equation that is of higher complexity than a directly integrable or directly integrable or separable ODE. And most of our processes that we're going to learn as you go throughout a differential equations course is to basically say, hey, I've learned something new. How could I tie something new back to something that's old that I've already learned? Okay. All right. So here's how we actually do this process here, or how we actually go about solving these types of equations. So first thing, given that our first order ODE is of this form here, and notice that I've put it in the form that I prefer. And we know that P of X and Y of X are functions of X, where P of X is known, Y of X is what we're actually trying to solve for. Okay. And of course, P of X and R of X here could either be functions or constants. Okay. So given that we have that information, we let this new parameter or function W, which we'll say W of X, be a new unknown function of X, such that whenever we take W and multiply it times Y here, is going to equal to this function big F of X. Okay. So we're just creating a new function here that's actually going to be the product of two functions, one of which will be our actual solution and the other one is something that's unknown. Now, it turns out that the function w, or w of x, is this integrating factor that I was talking about here. Okay, and so it is the integrating factor that makes the difference in simplifying this process for solving this type of equation. Okay, and so this is the function basically that we will use to multiply times both sides of our equations here to make this become a directly integrable type of equation. Okay, and so this is essentially what we're looking for here. Now, again, I know I said that sometimes it'll turn into a separable one, but we could literally, in some instances, turn separables into directly integrable ones. And so those are the ones that we're looking at. All right, so here we want to multiply our first order ODE on both sides by this integrating factor. Okay, so if we have our equation here, we just multiply w by each term, and this is what we end up having. Okay, so we start off by noting this. And the second thing that we note here is that big F of x, and let's go back to what that was here. Remember, this is big F of x here, is the product of these two functions here, the integrating factor and what our solution is going to be. Now, if we take the derivative of big F of x, notice that we're going to use the product rule here. So in using the product rule, we'll take the derivative of the first, or derivative of w times y, plus derivative of y times w. And that would be the derivative of what the function big F of x is, which is derivative of the product of these two functions. So if we note that, that's where we get that the derivative of big F of x is equal to the derivative of the product of w and y, and it looks like this. Okay, and of course, what I've done here is just switch the place of these to make it like that. Now, we see from steps 2 and 3 that what I am looking at here and what I'm looking at here looks very similar. Okay, and so our goal here in step 4 is to basically take equation 1 and equation 2, set them equal to each other so that you see if these two equations had to be equal to one another, what would have to be the same about them, term wise, in order for that to be true. Okay, so to do that, if we set them equal to each other here, I've taken equation 1, which is this first part, and then just said equal, and then did equation 2, where I use this part of equation 2 and this part. And notice here that w times r, and both of these are functions, would have to be equal to the derivative of the product of w and y. And we also see from these two that, of course, this first term is the same, but the second term is different by the derivative of w with respect to x has to be equal to w times p. Now, to see this a little bit more clear, I'm going to show this in a different view so that you can see how all this is related to each other. All right, so here what I've done is I've actually rewritten equation 1 and 2 together, just side by side by each other. And notice here that for 1 and 2, these two terms are the same. So I'm just going to X those out because those are the same. We also see that this y is the same here. So what you see left is that the derivative of w with respect to p has to equal wp. And we also see here that the derivative of the product of w and y is going to be equal to w times r. And so in order for equation 1 and 2 to be the same, we have to have these two relationships. Now, simply put here, it turns out that since we already know P, then I could use this equation to solve for W, okay? Hence, this is the equation that I would need to be able to find out what my integrating factor is, okay? After I find out what W is, I could take that information, put it into here, and since I have it here, and R is already known, essentially all I have to do at this point is just solve for Y. And so that's really, in a nutshell, the process of how to solve a first order linear ODE. If I can find what W is, then I can pretty much solve the equation. And notice here that because of the fact that I have an equation where, since I know what P is, I can actually find W with relative ease. So now you see why we have these two conditions that must be met, and they must both be true in order for equations 1 and 2 to actually be equal to each other, okay? Now in this note, again, the point that I'm making here is what I just said earlier. Since R of X and P of X are already known, then we can use this equation here to solve for W. And then after that, we can use the fact that we know what W is in this equation to solve for Y, which is going to be our solution. All right, and so if we actually do that process, this is what it looks like, okay? So looking here, we see that if we go through the process of actually solving for W, given that we know what P is, then, and again, I'm doing this the formal way, but I'll kind of come here and just do it in a way that's a little bit more simple here. So we have dW over dx is equal to WP. So basically here what we can do is rewrite this to where I have dW over W is equal to P dx. And then if you take the integral of both sides here, this will be natural log of absolute value of W. And this would be the integral of P dx. And here, if we actually did this, we would have some integration constant on the left side. But since I know I'm going to have integration constant both on the left and on the right, I'm just going to make it real simple and just put one constant over here on the right, just for simplicity, okay? Now, once that's done, then of course, to solve for W, here I could use my exponential rules here to make this both an exponential equation where the base is E. Of course, on the left side, this ends up being absolute value of W. And over here, I know that this could be rewritten as E raised to the integral of P dx times E raised to the C. And so here we see that with absolute value, just if I had like absolute value of X is equal to A, we know that this means that X is plus or minus A. So we're going to use the same type of thinking here. So this would mean that W would be plus or minus E raised to the C, because E and C are both constants. And this would be times E integral of P dx in the exponent. And for simplicity, we could just call plus or minus E raised to the C some constant A. And since we really don't care about what this constant actually is, because of the fact that in our original equation, we're going to take whatever W is and multiply it times both sides of the equation. So if I have A being multiplied on both sides of the equation, I can also divide both sides of the equation by A and essentially make that particular constant be reduced to 1. So it's not really important to have the constant there. So what we end up having is just e raised to the, in the exponent integral of p dx. And this is what our integrating factor is. Okay. And so that step that I was trying to show you here, that's essentially what it comes up to be. Now notice here that I chose not to rewrite a as plus or minus e raised to the c. I could do it this way. It really doesn't matter if you do it the way I just did before or here now, because the fact is that this part you won't really need. Okay. It's there just because, you know, it comes out in the whole process of doing everything, but in actuality, you don't need the plus or minus a part. What we're actually going to use is e raised to the integral of p dx. All right. So here in step 6, we just use this integrating factor like how I said before. And again, the reason for that is in the grand scheme of things, whatever that constant is going to end up being divided out anyway. So it really doesn't matter. Okay. Now, if we recall here that big F of x was the product of our integrating factor and the solution functions. Okay. And then, of course, we also know that the derivative of big F of x was going to be the derivative of the product of those two functions, which is equal to WR. And so from here, what I'm basically trying to show through this process that you see down here is that we can actually use this information here, mainly this equation here, to solve for what y is after we know what w is. Okay. And so that's essentially what you see me doing right here. So I'm saying that big F prime of x is equal to WR. And of course, I do the whole formal thing of multiplying both sides by dx. I don't necessarily have to do it this way, but this is the more formal way of doing it. I'll work it out for you in a more informal way so that you can kind of follow along as well. But once we're at this point, then of course we can integrate both sides by using an indefinite integral. Of course, integrating the derivative of some function, basically cancels out those operations. And so we just have big F of x. And then from here, we know that big F of x is just the same as the product of w and y. So if we want to solve for y, we have to divide by w, okay? And this is your basic formula here that you get. Now recall that this plus c here is the constant, is really a lumped up constant that comes from the integration constant from both of these indefinite integrals here. We just choose to write it on the right side for simplicity, okay? Now, as promised, I'm going to go ahead and write this in a more informal type of way so that you can see how we could get to this equation that we need a little bit quicker. Notice here that, again, our big F of x, if we take the derivative of it, is going to be equal to w times r. But of course, we know that another way that we could express the derivative of this particular function here is just to say we're going to do the derivative of w times y here. And if I made that equal to wr, then of course, what I could do here is just say, well, I want to integrate both sides, right? Well, to do that, I need to be able to still multiply both sides by dx here, since all these functions are functions of x. So if I had dx here and then dx there, and then I integrated, then of course with this I'm undoing a derivative, so I'll just have wy, and over here I would already know what w is, I would already know what r is as well, so that function would be whatever it's going to be. And of course, since both of these are indefinite integrals here, both of these would have integration constants. For simplicity, I'm just going to put it on the right. And then, of course, from here, I'll solve for y, which means I would have to divide both sides by w. And I would have this as a result. And notice that this integration constant here is not a part of the integral, okay? So you're going to be looking at it like that. And some people like to rewrite this divided by w here. It's just w raised to the -1, and then write it out like this. Again, you could here, yep, put that bracket in the wrong place here. And so if you write it like this, notice that w is divided by everything here. So when you write it as w raised to the -1, you have to multiply it times the integral of the product of w and r dx, plus then you got to multiply it again times this integration constant c. And so this is the formula way that I was talking about, that we can actually solve these types of equations here. But note that our w, which is our integrating factor here, would be e raised to the integral of p dx. And so if we did it the formula way, we would have to remember these two things, okay? All right, so the result from what I was just doing earlier would end up actually being this particular formula for what our y is. And of course, if we actually explicitly plugged in what the integrating factor would be, this is what our result would look like. Now, step 7 is really not, it really isn't necessary as far as new knowledge, but I just rewrite it this way to, at least in my opinion, to try to make it a little bit easier to remember the formulaic way of solving these types of equations here. So I allow the exponent that's in the formula for the integrating factor to be able to equal to h. And of course, if I apply that, then I'll have y is equal to e raised to the -h, all that times e raised to the integral of e raised to the positive h r dx, and then of course c times e raised to the -h as well here. So you see that e raised to the -h is multiplied by both terms, and of course we define h, or h of x, as just the integral of p dx. And so in short, all I'm saying here is that this is the formula that we could use. And this formula already has the integrating factor, which is just e raised to the h already tied into it. And there is a small mistake here that I'm going to fix. This should be e raised to the positive h. So don't know how that got to be negative there, but we're going to make that positive. All right, and so this in a nutshell, from a concept point of view, is how we actually solve first order linear equations, linear ODEs to be exact. Now, I know that this was a lot because we're trying to follow these formulas and derivations and whatnot. And that's why I wanted to do a summary to kind of make this compact, so that now, since we've actually gone through this process, you can kind of see in a nutshell what it is that we need to do, and we can just move forward from there with the examples. So in short, from our derivation process, we found that if we wanted to use the formulaic way of trying to solve a first order linear equation, then for our equation that looks like this, by over dx plus p of x y equals r of x, if we identify what p of x is and what r of x is, which we'll know, then of course we can just use this formula here where h is the integral of p dx and e raised to the h is going to be our integrating factor. And again, this should be plus here, not minus. I'm not sure why I kept writing that, but yeah, this should be a plus there. So again, the good thing is, yes, it's a nice formulaic way of remembering how to solve these types of equations. If you're the type that can memorize formulas, great. If you're not, then this probably won't work for you. So we'll have to take more of the traditional route. Okay. So I say, so is there another way for us to solve these kinds of ODEs without having to do the derivation process every time? And number two, to remember the formula above. Of course, the answer is yes. But what we'll have to do is essentially, remember what the integrating factor is and remember those two equations that we had to get from the process whenever we were doing the derivation of it to make that equation 1 and 2 that we talked about earlier sort of hold. Okay. And so if you don't remember the formulas, then you got to remember these two equations here. And so this equation will help you get your integrating factor. And then you use the result from this to be able to essentially get what your solution y of x is. Okay. So it's up to you. You can either remember these two equations here, or you can remember the formula. But in dealing with first order linear ODEs, we have to remember something. You just have to kind of pick your poison on what it is that you want to remember. All right, so for the last time, before we actually get into our examples here, we want to summarize this process of solving a first order linear ODE in steps. And of course, the very first thing that we want to do is identify that we have a first order linear ODE, whether it's in this form or this form. And of course, my personal preference is for you to be able to put it in this form here. Okay. Once we do that, we identify what the known functions p of x and r of x are. We use the information about p of x in this equation to be able to solve for w, which will be our integrating factor. From that, we note that this particular equation here will reduce to this. Now, why and how does that happen? Well, it happens that way because of the fact that we are multiplying w here, and this says q of x, but I think I used r of x earlier, so let me go ahead and correct that. So we're going to use r of x here. But we multiply that times w, and of course, this left side of the equation here, whenever we did the equating and all that stuff, one of the conditions that we had was that the derivative of the product of w and y had to end up equaling w times r. Okay, so the derivative of that. So the whole thing of taking your original equation here and multiplying it times w on all three sides. Once you do this, you would have to know that, yes, all this part here is going to have to collapse to just saying, what is the derivative of the product of w and y? That's essentially, what you're doing there. Okay. To me, it's easier just to say, hey, let's find the integrating factor. And, then after that, just use w here to be able to solve for what y is going to be. Okay. Being that you already know what r is. So I'm kind of taking out some of the extra steps that, depending upon other resources you look at, will include, because really I'm just trying to get to the point here. Okay. And again, I'm using repetition so that whenever we get to these examples, you'll kind of know in your mind, hey, this is what we need to do. This is what we need to do. All right. So once we find the integrating factor, use the integrating factor along with what we know r of x to be to basically solve this equation for y. And that's essentially the process. Okay. And again, we're going to do examples both using the formula and doing the process that I've just laid out here. All right, so let's get to it. Okay, so our first example here, we want to verify that each ordinary differential equation that we have is a first order linear one. And then afterwards, we want to solve the ODE for general solution. And we also want to determine the largest interval of interest. All that means is the values of x that are valid for the solution. And in the previous pages that we used, all I'm just trying to communicate here is we don't want to use this formula in this example at this point, okay? So we're trying to do this without using the formula first. So for this problem, here is our first order linear ODE, and we know that it's first order linear because of the fact that this particular ODE fits the profile of this ODE, where our P here is going to be 1 and our R is going to be e raised to the 3x. Okay, so that's what I have there. So we verify that is a first order linear ODE. Now, since we're using the non-formulaic way of doing this, we first need to find our integrating factor, which is found by this equation. And in doing that, since we already know what P is, we're just going to take this equation. Of course, P is 1 in this case, and we're going to solve for what W is going to be, okay? So if I do that, I integrate both sides here. And of course, I switched this around to where I make this dw over w equals to p times dx, and then do the indefinite integral. On the left side, I get natural log absolute value of w. On the right side, I just keep it as integral of p dx. And of course, we know here p is just going to be 1. And of course, we could rewrite it this way. Notice here, I have used the plus or minus a instead of just letting that be a. Really doesn't matter what this is, because whatever this constant is doesn't matter in the whole process. So we know that this is going to be our integrating factor, where this is 1. So of course, now I actually apply that here, and an integrating factor ends up being e raised to the x plus some constant c, which could be the same as a raised to e to the x, where a is just some constant. And thus, since we really don't need the constant part, the integrating factor is just e to the x. Excuse me. So once we're here, we have our first order linear equation here. And ideally speaking, I would want to multiply all 3 terms here by e to the x. Okay. And by me doing that, we know that the left side of this particular equation, all this is just going to simplify to the derivative of the product of w, which is our integrating factor, in y. Okay. So we just state that fact. And then of course, from here, we use what we know to be able to essentially solve for y. So we have, once we're here, if I integrate, then of course, this is going to be undoing the derivative of some function, which is just going to be what that function is. And of course, here we'll be doing the integral of e raised to the 4x dx. And of course, I've skipped some formality here to make the dx appear here, but we kind of know what was going to happen, so just wrote it. All right, and so for here, we just need to take the antiderivative, most general antiderivative of e raised to the 4x. So we have that here. And at this point, we know that the most general antiderivative of e raised to the 4x is just going to be e raised to the 4x divided by 4. And that comes from using the substitution rule here. And so I just explicitly write that out. And so once all that's done, then it's just a matter of taking our e raised to the negative x here that we had on the outside and multiplying it times what this result was, which is this. And of course, we distribute that to both terms. and we get that our y of x ends up being this particular function here. And notice here that e raised to the 3x, e raised to the minus x is continuous for all real numbers, and the domain of both of those functions is all real numbers. So because of that, this will be our solution, and we can plug in any real number x value into it. Okay, so for our next example, the first thing that we want to do is try to rewrite this particular equation into a form that hopefully is going to look like a first order linear. To do that, what we would need to do is divide both sides by x squared here. And the reason I'm saying that is because we would like to have something of this form. And so to do that, I will have to have this first term y prime all by itself, which means the x squared has to go away. How to legally do that, divide both sides by x squared. So if I have that, then here I have y prime plus x divided by x squared is just 1 over x times y equals x raised to the negative 2. And of course, we see that this equation satisfies a profile of this one. So we end up having a first order linear ODE. And where P is going to be equal to 1 over x, and R is going to be equal to x raised to the negative 2. So now that we've identified that, the first thing that we know is that the derivative of w, which is our integrating factor with respect to x, is going to be equal to w times p. And we've already said that p is just 1 over x, so we'll go ahead and put that in when necessary. So I'm going to first rearrange this equation here so that it looks separable. Okay. And so once we're at this point here, I can go ahead and put in my 1 over x here. So this will be dw over w equals dx over x. And we integrate, do indefinite integrals to both sides. And so from this point here, this will be, the left side end up being natural log of absolute value of w equals natural log of absolute value of x plus some constant. We could subtract natural log of x to both sides here. And then, of course, using our logarithm properties, this will just be natural log of w divided by x is equal to some constant. We can use our exponential rules here to rewrite our logarithmic equation as an exponential one. So we'll put the e's here like that. And we see that this results in absolute value of w divided by x is equal to e raised to the c. And of course, this would mean from our absolute value properties that we would have this, and we're going to let the plus or minus e raised to the c equal a, which means w really is just going to be a times x. And for simplicity, we let a equal 1. And remember, the reason why we're doing that is because it really doesn't matter what a is. When we multiply it times this equation in this form on both sides, whatever a is, I can just divide both sides by a and factor it out. So it really doesn't matter. So because of that, what's important to us is to know that w now, which is our integrating factor, is just x. Okay. And so now that we know this, we can use this to solve our equation here for y. So our integrating factor is just x. So number 2 is to say we know that the derivative of the product of w and y has to be equal to w times r. Okay. And of course, we know from here, if we write everything nice and formal, this could be the same as the derivative of w and y times dx, which is equal to wr times dx. And then you integrate both sides. And of course, from here, our left side will just end up being w times y. The right side here will be wr integral of that times dx plus some integration constant. Okay. And then from here, we could choose to go ahead and plug in what r and p are. I'm just going to wait till the end to do it. So y just ends up being all this business here divided by w. And of course, our w is just x. Our r was x raised to the -2 plus the constant, and then our w once again was just x. So of course here we know that all of this is just 1 over x. So our y will end up being natural log of absolute value of x plus this constant, all of that over x, which would just be natural log of absolute value of x over x plus c over x, if you wanted to keep it that way. And this would essentially end up being our answer here. Now, of course, for the domain of our function, we know that x can't be equal to 0. And since we have this absolute value here with the natural log, that would be the only real number value that would be restricted. If there was some way for us to either know through the context of this problem, if it was part of a word problem, or some other way where we just knew that x was greater than 0, then of course the domain of, or the intervals of interest for this particular solution would just be all positive values of x. But since we don't have that information, the best that we can say is that the only real number that's restricted is 0 from using it in the solution here. And so what you're looking at would be our actual answer here. So I'll just rewrite it here. So actually just be this plus cx raised to the -1, where x can't be equal to 0. So this would be our final answer for this example. Okay, so the next example will be an example where, of course, as you see, we have some trig functions in our first order linear ODE. I also am doing this example so that you can get an idea of how to actually find the intervals of interest, where the interval of interest for the solution to the differential equation is not as easy as just looking at it. Okay, so I wanted to show you at least an example of that so that you get an idea of how to approach being able to find that information if you're required to do so. So for this example, we see that our first order, we see that our ODE is already in first order linear form here. And we know that because this sort of takes on the profile of z prime plus pz equals r. Okay. And in this case, our p is secant and our r here is cosine. Okay. So you see that we have that, so it automatically fits. So we know it's a first order linear ODE. So that tells us that, hey, if we're going to be doing this and not use the formula, we'll first start off by using the fact that the derivative of W with respect to theta this time will be equal to W, which is our integrating factor, times P, which we know that that's secant. So now that we have that, we've kind of been through this process before. So in this example, since it's a little bit longer, I'm just trying to get to the point here. So we know that our integrating factor is going to be e raised to the integral of P d theta this time. And of course, P is secant, and the most general antiderivative of secant theta is just going to be natural log of secant plus tangent. And of course, we add some integration constant to it, and all that's in the exponent. Of course, we could rewrite this as e raised to the natural log of secant plus tangent times e raised to the c. And e raised to the c could just be some constant, and we'll name it a here. Now, remember that a really doesn't matter what a is, since we're literally taking the integrating factor and we're going to multiply it times, well, for all three terms of our equation here. So that means that that a would be in all three of these terms, and thus I could divide that a out. So it really doesn't matter what it is. So for simplicity, I just let it equal 1. And then from that point, we see that our integrating factor is just going to be e raised to the natural log of secant plus tangent. And of course, using our logarithm properties, we know that that's just absolute value of secant plus tangent. So from there, our second equation. So this was the second equation. And let me make sure that we note this here, that this is our first one. So after we find out what our integrating factor is, then we use that in this equation to be able to find out what our solution, which is z, is going to be. And of course, again, we've already sort of done this in a couple of other examples, so I'm trying to streamline this. So we know that taking an antiderivative of the derivative of wz is just wz. Taking an antiderivative of wr is just going to be wr, the product of that times d theta. And of course, to solve for z, just divide both sides by w. This is what we get. And then we just plug everything in. So of course, our integrating factor is absolute value of secant plus tangent. R is going to be cosine theta. And so here in this next step, notice that I drop the absolute values going from this step to this step. Okay. And I do it because I want to know specifically what values of theta will allow this to happen. And so it turns out that this interval here, and it really is just it's a continuation of intervals. So you can say, this when n is equal to 0, union with this when n is equal to 1, union with n is equal to -1, union with n is equal to -2, and just keep going on and on. All of those intervals union together would be the actual single interval on which secant theta plus tangent theta would be non-negative, because that's really what we're saying here whenever we have the absolute value of secant plus tangent. And so I'll show you after we actually arrive at the solution why this actually is. And I'm going to use two different approaches to do that. So once we have this situation here where we plug everything in, of course, we'll take cosine and just distribute it across both terms here. And that's another reason why I wanted to go ahead and drop these absolute value signs and figure out what theta would be in those instances, because technically I can't go and do this unless I know when cosine is going to be non-negative. Okay, so I would have to do that with that assumption in there. So that's, again, another reason why I wanted to do this. So once we're here, we see that all of what we have here with the integral just simplifies to 1 plus sine theta, taking the integral of that times d theta. And of course, the antiderivative of 1 in terms of theta is theta. Antiderivative of sine in terms of theta is negative cosine theta. And of course, we add the integration constant there since this is an indefinite integral. And all that gets divided by secant theta plus tangent theta. So in essence, that is our answer. And so you could choose to write it this way, which is a preferred way, or you could write it this way if you like. But here again, we see that the interval of interest, meaning the values of theta that makes sense for this, that essentially say, hey, if I had the absolute value of secant plus tangent here in this problem, what values of theta would that actually be valid for, okay? And so now I'm going to explain how I actually came up with that particular interval. All right, so one way in which we can determine that that interval is what it was that if we note that 1 divided by absolute value of secant plus tangent, we find out that that's actually an identity for something else. And so I just kind of go through the process here of rewriting this so that we eventually get the absolute value of cosine theta over the absolute value of 1 plus sine theta, okay? And so in seeing this, the approach that I took here when I first thought about it was, well, let's just look at a graph of what cosine theta and a graph of what 1 plus sine theta would be and find out an interval or two for where both of those functions would be above the theta axis, okay? And so if you look here, I've done exactly that. And of course, we see that our graph for cosine is above the theta axis in between here, which is when theta is equal to negative pi over 2, and here theta is equal to pi over 2. Of course, that would happen again over here in between 3 pi over 2, and if this came down, this would be 5 pi over 2 here. Same deal here. This would end up being a negative 3 pi over 2, and this would be a negative 5 pi over 2 over here towards the end of the screen. So for those intervals, excluding the n values, our graph would be above the x-axis for cosine. If we did the same thing for sine, we see that only when sine actually, sine plus 1, only when it hits the theta axis here is when it would not be in that interval. And of course, this point here is a negative pi over 2. This point here is a positive 3 pi over 2. And if we were to go on and draw successive periods for this, we would see that if we counted 4 half pi units, we would get to the next one to where that would be true. So here, since this is 3 pi over 2, then I would count 1, 2, 3, 4. That would be 7 pi over 2 when it would do like this again. Of course, it would hit and then go back up. So my point here is that just looking at this from a graphical perspective, we know that cosine is strictly above the theta axis here for this interval, this interval, this interval, and we just keep on going. Where, of course, this interval is this first one here. This interval is this second one here. This one is this third one here, okay? If I did the same thing for 1 plus sine theta, when is that above the x-axis? Notice that it's not going to be, it's going to be everywhere except for where we have x-intercepts. And of course, we have x-intercepts at negative pi over 2, so that's why we see that there. 3 pi over 2, that's why we see that there. 7 pi over 2, see that here. Negative 5 pi over 2, see that there. So all these places where we would have x-intercepts for 1 plus sine theta would be what we would have to exclude, but we can include everything else. Now, the point here is that since we are looking at cosine of theta divided by 1 plus sine theta, we have to find the values of theta that work for both of these, meaning that what are the collection of theta values for where both of them simultaneously are above the x-axis. And so that turns out that since the interval in between negative pi over 2 and pi over 2 is smaller than the interval of negative pi over 2 to 3 pi over 2, and these intervals kind of follow suit with the respective one from 1 plus sine theta, it turns out here that cosine of theta divided by 1 plus sine theta is going to be above the theta axis for the intersection of this interval, as well as the intersection of these two intervals, as well as the intersection of these two intervals. And of course, for all of these, the first one here is the smaller one out of the two. So that's why we get this result here. Now, if we were to write this in a compact way, basically what you see happening here is that I'll have a negative pi over 2 and then 2 pi units later, whether you go to the left in this situation or if you go to the right in that situation of negative pi over 2, you're going to find another interval starts. Okay. And then, of course, here, the length of this particular interval here is roughly pi units. So that's why you have these corresponding values here. So we see that this particular function is going to be non-negative or above the theta axis whenever we rewrite it this way. So basically, whatever this is, skip 2 pi n units. And of course, whatever this is, pi over 2 plus 2 pi n units, where n is an integer. And this is just the same thing that is, but I just wrote it in a way to where you can just quickly plug in values of n and quickly see what the next interval would be. Okay, so that was the way that I knew in working this problem once I got to that, what that interval would be. Okay. And of course, just kind of finish it out. Thus, the interval of interest for the theta values that are valid for the solution z of theta is just going to be this interval here. Okay. Now, that was one approach. The other approach I took to think about this, and I did it 2 different ways just to make sure that I was thinking about it correctly, is that if we just look at the graph of secant and tangent on its own, and of course, the reason I'm doing that is because the issue here is to figure out when is secant theta plus tangent theta going to be non-negative, meaning what are the values of theta that make that happen. If we look here, we see that the graph of secant in between negative pi over 2 and pi over 2 is always going to be 1 or higher, whereas tangent, that's not always the case. Matter of fact, tangent doesn't get to be at a value of 1 until it hits pi over 4 radians, which is the same as 45 degrees here. So we see that from here on up, this is going to lag behind secant. So that means the graph of secant is always going to be above the graph of tangent in between negative pi over 2 and pi over 2. Okay. Now, we know that secant and tangent are periodic. So if I was to draw another period for secant and another period for tangent, it turns out that in between 3 pi over 2 and 5 pi over 2, I'm going to have a similar graph where graph of secant is going to look like this, graph of tangent is going to look like this. And, for that, I know that secant is going to be above tangent. And then, of course, I can skip over some more, draw some additional periods, and I see that that would be the same thing. Okay. And so essentially, I'm showing you these graphs here just to show you that secant theta will be greater than tangent theta for this particular interval, but it'll also be greater than, secant will be greater than tangent for this interval, this interval, this interval, and this interval if we actually was to draw everything out. And if you notice, these are the same intervals that I had in the previous way I looked at this. So I know that that can be represented this way as well. Okay. Now, again, the reason why I'm going through this, some people may call this overkill, but I'm going through it because you actually use differential equations to use them. Okay. And if you're going to use them, then you need to know what independent variable values, in this case your theta values, you need to know exactly what can you use. Okay. There's no point in solving a differential equation to get an answer for it, and then you don't know what values you can actually plug into it. And so that's why, at least in these videos that I'm making for you, and depending upon what textbook you may be studying from, they make a point to make that something that's important for you to keep in mind as you solve these differential equations. So in this next example, and this will be the last example that we will actually solve this via what I call the traditional way, where we're using the equation that the derivative of w with respect to x is equal to wp, and that the derivative of the product of w and y is equal to w times r. Using that two-step approach, this will be the last example for that. The examples that I do afterwards will be utilizing that formula that I mentioned earlier at the beginning of this video. So for this example, same kind of thing. We want to get this particular equation in the form of dy over dx is equal to p times y equals r. And so to do that, we would need to divide both sides of this equation by cosine. If we do that, then we would just have dy over dx. And that would be plus sine. Let me just go ahead and write it in here. Yep, so that way everyone will kind of know what I'm doing here. So if we do that, we'll have dy over dx for the first term, tangent of x times y for the second term, and secant of x for the term on the right side. And so from that, we see that our tangent here would be what the p is. Our secant x would be what r is. So this is first order linear. All right, so now that we've established that, so now we can go ahead and solve. So our first step is to take the derivative of w with respect to x is going to be equal to w times p. And again, we already know that this essentially means that we're going to find the integrating factor. Okay, and so the integrating factor will end up being w is equal to e raised to the integral of p dx. And I'm going to leave off the plus c now because that part really doesn't matter, and I think I've said it enough in some of the other examples for you to catch on to that. And so here the p value, that's going to be tangent and of course the antiderivative of tangent, it can be one or two representations. One is minus natural log or absolute value of cosine x, or you could say it's going to be natural log of secant. So it just depends upon what you feel more comfortable expressing it as. Yep, so you can use either one of these two. I know personally, what I'm going to do is just leave it as secant here because I don't want to forget about the minus sign that may be here. So therefore, w, if I just do e raised to the natural log of absolute value of secant. This is just going to end up being absolute value of secant. All right, so now we need to apply the second equation. Of course, that second equation says the derivative of the product of the integrating factor in our solution y. Take the derivative with respect to x, will end up being the same thing as the integrating factor times r. And if we do that, then of course we know that wy just ends up being the integral of wr times dx. And thus, we know that y is just going to be all this business here. And I forgot to put the plus c here. I need to put that there, because whenever we do the antiderivative of this part, it has a plus c in it. Well, it has an integration constant, and of course, whenever we do the integration constant on this side, it'll be a plus c in it too. So I'm just going to put it here, and we'll divide this by w. So now we just fill in everything that we know. And of course, the integrating factor is secant, or absolute value of secant rather. And for r, forgot what we said r was, so let's look at it. It was secant as well. Okay. And that would be that dx plus some integration constant here, and we divide all of that by w, which is absolute value of secant as well. So at this point in our problem, one thing that I do want you to notice here is that we have absolute value of secant, but then we also have just regular secant. So in order for these to work together, we're going to have to kind of concede to the absolute value of secant, which means that we need to find the values of secant, meaning the values of x for secant, to where secant is going to be non-negative. Okay, so I'm going to rewrite what I have here as follows. So basically, I'm dropping the absolute value signs here. But I need to take into account when secant is actually non-negative. Now, if you remember the previous example that we had, the interval that we came up with for that particular problem is the same one that we would have to use here, because we're essentially tracking whenever secant x in this case is going to be above the x-axis. So here, what we know is that x here is going to be this interval where we had 4 pi n minus pi over 2, 4 pi n plus pi, all that over 2. If I can get my eraser to work, I'll write it. So 4 pi n plus pi, all that over 2. And of course, n would just be an integer. So it'll be all those little intervals kind of unioned together. Okay. So we're going to work this problem from this point on, knowing that these are the x values that will be valid for. Okay. And that's another reason why, again, it's important for you to be able to deal with situations like this and know, hey, what values of x can I actually plug into here? And it makes sense. All right, so I'm here at this point. What we'll do is just continue on here. So now what we need to do is figure out what the antiderivative of secant squared is. And of course, that's just tangent. So we got tangent of x plus our integration constant, all that divided by secant. And then of course from there, if we go ahead and write all this out, we know tangent is sine over cosine. And of course, secant is 1 over cosine. So it's going to give you something like this. And of course, we got c over secant. And of course, the reciprocal of secant is cosine. So we'll just do this situation here. Okay, and so, oh yeah, this should be 1 over secant, not 1 over cosine here. The reciprocal of secant is cosine, but what I'm essentially doing here is trying to divide sine here divided by cosine. So I need to have cosine and secant in the denominator together. And of course, from there, we know that cosine and secant are reciprocals of each other. So these two things just work together to reduce to 1. And what I have left here is just sine of x plus c cosine of x. And so this would be my final answer. So I'll just go ahead and rewrite it. So therefore, y is equal to sine of x plus our constant c times cosine of x. And of course, x here, the values that would make sense for this would be what we just mentioned earlier. And I'll just go ahead and rewrite it all out. And of course, n in this case is just an integer. Okay, so the next 4 and final 4 examples I'm going to do will be examples to where I'm actually going to use this formula here to be able to solve first order linear ODEs. So we're not going to go through that whole process of, the 2 differential equations and we got to solve that. We're just going to pretty much go straight for the jugular here. Use H, of course, identify what P and R are going to be. Use H to find that, and then use H and R in this formula to be able to find out what our solution Y is. We also have some initial conditions here. So I also wanted to do these examples since we have a little bit more to do at the end. I wanted to do that and make it shorter so that we could focus on the initial condition parts too. All right, so just as we always start with these types of problems here, if this is supposed to be a first order linear ODE, then I want to get this in a form to where I recognize that it actually is a first order linear ODE. In this case, I need to divide numerator and denominator by x. And so this means that I have y prime plus 1 over x y equals e to the x divided by x. And since I divided by x here, I know that x will not be able to be greater than 0. I've stated here that x is greater than 0. So because of that, I don't have to worry about it. And so I'll put this in to make the problem a little bit easier to do, because if we just left it as, x is not able to equal to 0, then I would have to get into piecewise functions and didn't really want to do that here. All right, so we see that, let's get the eraser going here. So we see that we have this in this form, and this will meet the profile of a first order linear equation. And here, that's the case, then of course our P will be 1 over x, and our R will be e raised to the x divided by x. Okay, so of course our first step here is to find out what h is, integral of p dx. And P, we said, was just 1 over x dx. So this is going to be natural log of absolute value of x. And we'll just say that it's natural log of x since x has to be greater than 0. So from that, we need to use this formula here to figure out what our solution is going to be. And I'm just going to write everything in, and then we'll take care of it. All right, so now that we have that, we can simply just write everything in. So we have e raised to the minus natural log of x, all that times integral of e raised to the positive natural log of x, times r, which is e to the x divided by x, all that dx plus c. Of course, here, e raised to the negative natural log of x, we could rewrite this as e raised to the natural log of 1 over x. Of course, we can do that because if we take negative natural log of x, that, use logarithm properties, we can rewrite it this way. And of course, x raised to the negative 1 is the same as 1 divided by x. So that's why we're able to do that. All right, so now that we have that in place, we just figure out what y is. So, of course, e raised to the natural log of 1 over x is just 1 over x. Here, e raised to the natural log of x, that is just x. And this x will reduce to 1. So essentially just going to have integral of e to the x dx plus integration constant. The antiderivative of e to the x is just e to the x plus integration constant. And so this ends up being e to the x divided by x plus c divided by x. And of course, we know that x has to be greater than or equal to 0. So that is what our y would be. So let's go ahead and note that now. So y of x is just e dx over x plus c over x, x greater than 0. And so now from here we can apply our initial condition. So here's the general solution. So our initial condition, we had when x is 1, y is 2. And so all we got to do is just plug that in now. So we'll have e raised to the 1 over 1 plus c over 1. All that's equal to 2. So that just means that e plus c is equal to 2, which means c is 2 minus e. And our final answer here is just that y of x is equal to e to the x divided by x plus 2 minus e over x, where of course x is greater than 0. And that will be our solution for this problem. So for this next example, what I'm actually doing here is I'm taking an electrical engineering application, and we see that we have an equation that sort of describes the voltage in a loop in a circuit. And so one of the things that we know in electrical engineering, KVL or Kirchhoff's voltage law, is that All the voltages in a loop in the circuit have to add up to equal to 0. And so another way of saying that is if we look at E as electromotive force or voltage, the voltage source has to be equal to all the voltage drops. And so what you're seeing here is a voltage drop across a resistor. This is a voltage drop across an inductor. And those are resistors and inductors are elements that we use in electrical circuits. So here what we're trying to do is basically come up with an equation for the current going through a loop, a voltage, or just a loop in a circuit period. And we know that I sub 0, L, R, and E are all going to be constant values. Now, we don't really have to know about that to do this particular problem. The only thing that we do need to know about is the fact that we recognize that this is a first order linear ODE, and we can do that by dividing both sides by L here. And if we do that, we see that we get di over dt plus R over Li equals E over L. And remember, R, L, and E are all constants here. So since this is first order linear, then we also know that P and R will be important to us. Our P is R divided by L, and our R is E divided by L. So now that we have that, we can just use our formula. And of course, we know H integral of P dx, and P in this case is R divided by L. And remember that R and L are both constants. So any constant, if we take the antiderivative of a constant, it will be just that constant. And so here I do have X, but I'm going to change that right quick. I'm going to change from it being dx, I'm going to change it to t, just because in reality we actually use t to mean time here. So I'm going to change that to make this a little bit more realistic. So that would be RL times t, where t is equal to time. Again, we don't worry about the integration constant at the end here because it's immaterial in what we do. So now that we have that, then we know that y is equal to e raised to the negative h times integral of e raised to the positive h times r times dt plus c. And again, I'm using t here to represent time because for this application, it would be looked at in time instead of as x. All right, so once we have this, then we just have e raised to the negative RLT times integral of e raised to the h, which is positive RLT, times r, and of course our r is e raised to the L dt plus integration constant. Okay. All right, so here, remember that e divided by L is a constant. So what I'm going to do here is just factor out the e over L part here. Just leave that here. The r divided by LT in the exponent there. dt plus that. And so remember that when we do e raised to the r divided by LT, that's very similar to, and I'm just using an example here, of saying we need to take the antiderivative of e raised to the 3t. Okay. Now, if we did this, of course, the answer to this would end up being e raised to the 3t divided by 3 because of the substitution rule. And we kind of know what it ends up being because this is one that's very common. So here, notice that we got a 3 here. This is essentially 1/3 times e raised to the 3t. So when I take the antiderivative of this, it's just going to be the reciprocal of r divided by L, which is L divided by R, times e raised to the RLT. Okay, so we know that in this next step here, that's what it's going to end up being. So we'll have e divided by L times L divided by R, e raised to the RLT, and then plus that integration constant. All right, so now at this point, just need to multiply everything through. So if we look for this first term, we're going to have e raised to the negative RL times t times e raised to the positive RL times t. These two things will multiply together to just be 1. So I don't have to worry about that in the first term. Also in the first term, these L's will reduce to 1. So all I would have left in the first term here is just e divided by R. Okay. For the second term, I have a constant, and then I have e raised to the R, negative R divided by LT. Okay. And so this is what our resulting solution would look like. So this would be y of t, and I'm going to rewrite it here. And I'm going to rewrite it this way. And the reason I'm doing that is because this E, which stands for electromotive force or voltage divided by R, is essentially current. So we could, even though this is not absolutely correct, but I could say that, hey, this is going to be the initial current for this particular situation here. So that's why I just named it I sub 0 there. Now, oh, actually, you know what? I forgot I have this initial condition here. So let me not do that because it'll fall out the way that I want it to if I don't name it that way. So yeah, I'll just keep it as E divided by R, and you'll see what I'm talking about here. All right. So here we notice that our I sub 0 here, or I of 0, is just going to be I0. Or I sub 0 rather. So basically for this current equation that we're coming up with, and I've been using Y here, but I really need to use I since that's what it actually is. So I'll go ahead and erase that. Keep everything consistent here. So this would be I, and then I of t. And so, of course, from here, if we use the initial condition, so we'll just call it IC, I of 0 is equal to I sub 0. And that's going to imply here that I sub 0, which is what that's going to represent when I plug in 0 here, it's going to be E divided by R plus C e raised to the 0. And so here, e raised to the 0, that's just 1. And so C would just end up being I sub 0 minus E divided by R. And so once all that's done here, then we can come back and just say that I of t is just going to be E divided by R plus I sub 0 minus E divided by R, E raised to the minus RLT. So this would be our final answer here. And now that we have this particular equation for the current in a loop of a circuit, and I'll go ahead and draw what this is. We can also quickly talk about what this equation is actually trying to communicate. So if I actually had this drawn in a circuit, it would look something like this, where here is your resistor, this is your inductor, and what you're actually trying to find out is the current that's in this loop here. And so, of course, the current would go around like this. And so notice here that when t is equal to 0, like how we said before, our I of t is equal to I sub 0, which is just some initial current value, okay? Now, if we looked as t approached infinity, if we took infinity and plugged it in here, we know that infinity times a negative number is just going to be negative infinity. And of course, e raised to the negative infinity, that goes to 0. So this whole term here would end up going to 0 as t approaches infinity. And all I would have left is E divided by R, or the voltage divided by the resistance of this resistor right here. And that's really basically telling us that what this inductor is doing is it is impeding current flowing through this particular circuit here. But as time goes on, the resistance that this particular inductor is, I guess, resistance to current flow is sort of wearing off over time based upon what we're told here. And so we'll have some initial current here. And again, if this initial current is larger than this, then of course, this initial current will die down to this over time. If it's vice versa, then this particular current here will build up to this over time. Okay, and it really just depends upon what the numbers are, but that is what this particular equation is trying to communicate to us. And so, of course, I could use this ideally for any time where t is greater than or equal to 0. So it really wouldn't make a whole lot of sense for me to use negative values for this, since I'm trying to track how the circuit operates from some initial time moving onward. And again, that's what I meant in the earlier examples when I was saying, hey, once we actually find out what the solutions to these differential equations are, we need to know what values we can actually plug into. So for our next example, we want to solve this particular initial value problem. And we see here again, this is probably going to be a first order linear. And we can divide both sides by x plus 1 to get it into the form that we need to have it in. So if we do that, we'll have dy over dx for the first term, plus 1 over x plus 1 times y for the second term. And for the term on the right side, we'll have natural log of x plus 1. And of course, in this case here, notice that x can't be negative 1, but we also see here, because of the natural log, that x has to be greater than 0 as well. So we're going to note here that x has to be greater than 0. And that will help us to do some simplification to make life a little easier for us down the road, since we are noticing this now. All right, so because of this, this is a first order linear ODE. And we know from this that our P ends up being 1 over x plus 1, and R is going to be natural log of x over x plus 1. And so since we're using the formula for this, we're going to say that y is equal to e raised to the negative h times integral of e raised to the h times r times dx plus c, where h is going to be integral of p dx. So h integral of p dx, which is just integral of 1 divided by x plus 1 dx. If we use substitution rule here, we'll see that this just ends up being natural log of absolute value of x plus 1. And since x has to be greater than 0, we can drop the absolute value signs and just say that this is going to be natural log of x plus 1. So now from there, y ends up being e raised to the negative natural log of x plus 1. All that times integral of e raised to the positive natural log of x plus 1 times r, which is natural log of x over x plus 1 times dx, and then plus our integration constant. Now from here, we know that this minus here can be brought up to the exponent of the x plus 1. And here we know that natural log of x plus 1 raised to the negative 1 would just be the same as natural log of 1 over x plus 1. So if I had e here like this, the result would just be 1 over x plus 1. So that is what belongs here. E raised to the natural log of x plus 1 would just be x plus 1. And that multiplied times natural log of x over x plus 1 times dx. All that will reduce to 1. And then we add the plus c. So now at this point, all we end up having now is that this is going to be equal to 1 over x plus 1. And then this will be the integral of just natural log of x dx plus c. All right, so the antiderivative of natural log of x, you could do it by doing integration by parts, but it's, again, one of those that after you learn how to do basic integration, using integration by parts, it comes up a lot. The antiderivative for that one just ends up being x times natural log of x minus x. And then, of course, we have our integration constant there. And this is essentially what our answer is. So we could write it in compact form. But once we're here, then it's just a matter of just using the initial conditions or initial condition to be able to figure out what our integration constant is. All right, so what we have here is our general solution. All right, and so we want to apply the initial condition. And our initial condition here is when x is 1, y is 10. So if we do that here, well, y, which is 10, and that equals to 1 here. So that's 1 times natural log of 1, which that'll end up being 0, minus 1 plus c over 1 plus 1. And of course, 1 plus 1 is 2. So if we do some cross multiplication here, put this over 1, we'll have 2 times 10 is 20. And over here, 1 times -1 plus c is just going to be c minus 1, which means here if we add 1 to both sides, c is 21. So now we know what our integration constant is, and we can state what our final answer is for this problem. So y of x will be x times natural log of x minus x plus 21, all that over x plus 1. And again, x here would have to be greater than 0 in this case. And so this is our final answer for this particular problem. Okay, so this is our final example. And so I wanted to throw this example here in here because it has a couple of different things that we haven't seen all work together that we do need to see at least an example of that happen. So first, we see that we have a first order linear ODE. Second, notice that the ODE is defined in terms of a piecewise function. So we have to remember how to deal with that. If you have forgotten how to deal with functions that are defined as piecewise functions, I do have a video on that. If you're taking one of my courses, then you should have seen that video before watching this one. But if you're not taking one of my courses, then of course you can always look it up. Just look up solving differential equations with piecewise functions, and I'm pretty sure mine will be one of those that comes up. The third thing is, of course, we have an initial condition here. Okay, so we got the thing of first order linear, initial condition, and being piecewise, all kind of working together at the same time. Okay, so with that being said, what we're going to need to do here is actually solve two problems. Okay, so the first problem that we will have to solve would be dy over dx is equal to dy over dx plus 2xy equals x, because that's the first piece in the piecewise function. The second problem that we will have to solve is dy over dx plus 2xy, and that will equal 0. Okay, and so of course for this first equation here, we will note that x has to be in between 0 and 1, including 0, not including 1. For our second one here, x will have to be some value that is 1 or larger. Okay, and so in solving each of these separately, we're going to get solutions, but we also have to make sure that since this equation was defined as a piecewise function, our solution needs to be continuous, and we may have to do the limit of one solution on the left, other solution on the right of x equals 1 to make sure that they sort of hook up with each other so that the function is continuous at x equals 1. So that will be one of the last things we'll be considering towards the end of this problem. All right, so let's solve equation 1 first. So if we do that, we have dy over dx is equal to 2xy equals x. And in this case, of course, we know that both of these are first order linear, so let me go ahead and write that here, first order linear. So here our p in this case will be 2x, and our r is just going to be x. So the formula that we'll use here is y is equal to e raised to the negative h times integral of e raised to the h times r times the x plus c. And remember that e raised to the negative h is multiplied times all of that. And our h is just integral of p dx. And here we see that p is just 2x. antiderivative of that. And of course, we're not doing the plus c part. It's just going to be x squared. Okay. So because of that, we'll have y is equal to e raised to the negative x squared times integral of e raised to the positive x squared times r. Of course, r is just x times dx plus c. And if you notice here, for our integral, we have a situation here where we can actually use the substitution rule, because if we let u equal x squared and then take the derivative of x squared, that's just 2x. And of course, we have this x here, so we know that the substitution rule would work. So we're going to say let u equal x squared, and then that implies that du is equal to 2x dx, which also implies that 1/2 du is equal to x dx. And of course, we see x dx here, so that can be replaced by 1/2 du, and x squared can be replaced by u. So have everything that we need. So from here, e raised to the negative x squared, integral of e raised to the u times 1/2 du plus c. And the antiderivative of e to the u is just e to the u. Of course, we factor out the 1/2. Then we have the plus c at the end. And u, of course, is just x squared. So what this tells us, after we multiply through the e raised to the negative x squared here, that y for this situation would just be, for that first term, it's just going to be 1/2 all by itself here. Just trying to get my eraser working. All right, so now that we got this, so we got the eraser working here. Let's turn it off. Okay, all right. So now, of course, with this first term, we have the e raised to the negative x squared and e raised to the positive x squared being 1. So that's just going to be 1/2 plus c e raised to the negative x squared here. Okay. And again, we know that this is true as long as my x values are in between 0 and 1, excluding 1, including 0. All right, so now what we'll do is solve our next equation, which will be the next piece of the piecewise function. So for this one, we have dy over dx plus 2xy is equal to 0. Okay. And so for this one, this is a first order linear as well. But if you notice that since this is equal to 0, I could just rewrite this way. To xy here, and of course from here, if you can tell, this could actually be rewritten as a separable ordinary differential equation. And so if I was to rewrite this to where everything in terms of y is on one side, everything in terms of x is on the other, then you see that this is essentially a separable ODE. Of course, I could just integrate both sides like that, and we see that on the left side we would have natural log the absolute value of y, so a little therefore there. On the other side here we have -2, and the antiderivative of x is going to be x squared over 2. And of course, plus some constant there. So this would end up being natural log of absolute value of y equals minus x squared plus some constant. And if I was to try to solve for y on its own, then of course here this would be, we'll use our exponential rules there. And this would end up being absolute value of y, which is equal to a times e raised to the negative x squared. Well, we won't do that yet. So we just call this e raised to the c, and then we'll do the renaming of the constants in the next step. Okay. So now from here, that means that y, according to our absolute value properties here, would end up being plus or minus e raised to the c times e raised to the negative x squared, which means that y here would be a e raised to the negative x squared, or our a here would be plus or minus e raised to the c. Okay, and so that would be what our second solution would be. So let's go ahead and make sure that we know what solutions we're looking at here. So this would be the solution for our first piece of our piecewise function. And I'm going to rewrite this one and circle that just so that we have this as a frame of reference. And this is the one where x has to be greater than or equal to 1. All right, so this is our solution to the second piece of the piecewise function. So now that we know what our solutions are for the first and second piece of the corresponding piecewise function in our differential equation here, we do need to go ahead and apply the initial condition. So let's talk about that. So here, of course, our initial condition was y of 0 is equal to 2. So I'm going to go ahead and rewrite that down here. So I want to apply the IC. Now notice that the initial condition goes along with our first solution, not our second. Okay. So when we apply this initial condition here, we can only apply it to this first piece. Okay. So here, when we apply it, y of 0 equals 2. That implies that we have 1/2 plus c e raised to the 0, and that is going to equal to 2. And of course, e raised to the 0 is 1. And if we want to get rid of this fraction here, we can multiply both sides of this equation by 2. And if we did that, of course, we would have this situation here. So we would have 1 plus 2c is equal to 4. And from that, that would be 2c is equal to 3, because we'll subtract 1 from both sides. And if we divide both sides by 2, we get c is equal to 3/2. So what we're actually seeing here is that from 1, and I'll go ahead and 1, y is actually equal to 1/2. let's get this eraser right here. So it'd be 1/2 plus 3/2 e raised to the negative x squared here, okay? And so that will be our updated function for what part 1 is going to be. And of course, again, this is for values of x that are in between 0 and 1, including 0, excluding 1. All right, so now that we have all of this together, we have this piece, and so now, of course, notice that how y of x will look will be different depending upon if we are to the left of 1 or to the right of 1, okay? And we need to ensure that this particular function here is going to be continuous. So what that means is we're going to have to find a value a here such that whenever x is equal to 1, it's going to be equal to the same as the limit of this particular function as it approaches 1. But that's coming from the left. So how would we do that? We would have to say that basically the limit as x approaches 1 from the left of this version of our piecewise solution this will have to be equal to the limit as x approaches 1 from the right of our other version of our piecewise solution. Okay, and so in doing that, we can figure out what a is actually going to be so that these two pieces of our piecewise function will be continuous at x equals 1. So here, this implies that we have 1/2 plus 3/2 e raised to the negative 1. And on the right side here, we'll have a times e raised to the negative 1. And of course, we can do that because 1 is in the domain of both pieces of the piecewise function, interpreting them as functions. So here, all we need to do is just solve for a. And of course, to solve for a, we can just divide both sides by e raised to the negative 1. And this would end up being 1/2 e raised to the negative 1. For the second term, the e raised to the negative 1s will reduce to 1. I'll just have a here. And of course, e raised to the negative 1 in the denominator is the same as e raised to the positive 1 in the numerator. So we can just look at it like this. And thus, a would just be e plus 3 divided by 2. And so that would be what the value of a would have to be in order for this function to be continuous at x equals 1. All right, so it looks like we're at the final part of this particular problem because we have all the information that we need to state our non-constant solutions for this. But notice we didn't look at our constant solutions, okay? And I want to take a look back at that only because the number, I'll say the first piece of our piecewise function, its corresponding ordinary differential equation could be rewritten in a way to where we could find constant solutions. And so let's go back and take a look at that. So for our first piece, and I'll write this in a different color so that you'll know that this is a little bit different than what we've looked at before here. So notice that here in our first piece that if I was to rewrite this equation, I could rewrite it as dy over dx is equal to x minus 2xy, okay? And of course, since I have x in both terms here, that could factor out to x times 1 minus 2y, okay? Now, the first thing that this shows you is that, number one, although this is a first order linear ODE, it is also separable, okay? And it's separable because I could have actually taken the approach of saying, rewriting this as dy over 1 minus 2y here on the left side of this equation. And on the right side, it could have been just dx over x, okay? So this was a separable equation, but as you can see, we do have separable equations that are also first order linear, okay? Not all first order linear equations are separable, but we do have some separable equations that are first order linear. And that was one of the reasons why I made comment to sometimes our linear ODEs end up being separable as well. And this is one of those examples. So other than that, though, we see if we're looking for constant solutions, we need values of y that will make our derivative go to 0. And of course, we need that because we know that the derivative of any constant value is 0, okay? So here, since this is a function of x times a function of y, from here, I know that dy over dx would be 0 when 1 plus 2y is equal to 0. And of course, if I was to solve that equation here, we would see that y equals 1/2 would actually be a constant solution here, okay? So in addition to the answers that I have here for our first piece here and our second piece of our solution, of course, where a is e plus 3 divided by 2, I also need to include the fact that y would have to be 1/2 at some point, okay? And so if I look here, I know that if I'm looking to see is there going to be an x value that would actually allow one of these pieces to be 1/2 for it, I don't think so. And of course I say that because for piece 1, if we let x equal 0, which is the lowest y value it could be for this, if I plug that in here, I'm going to have e raised to the 0, which is 1. And then, of course, here, we would have, so all that would just end up being 2 at this point. And I guess in between 0 and 1, I couldn't plug in 1, but I know that if I could, here I would have 1/2 plus 3/2 e raised to the -1 here. And if I looked at that value there, I don't think I'm still going to get to 1/2. And so I say that because if I was to write this here, this would be that over this. And whatever this value here is, it is not going to be 0, of course. So it's going to be 1/2 plus a value that's larger than 1/2. So not going to work. So I'm not going to have a value in between 0 and 1 here that will give me y equals 1/2 here, okay? So again, we know for this first piece, there's not going to be a value of x that will work to give us y equals 1/2. If we consider the second piece, the second piece here, we know that this a here, and I'll just go ahead and write it out. This a is going to be e plus 3 divided by 2, and this would be times e raised to the -x squared. We would have to ask ourselves, all right, is there some value of x that will be larger than 1 that will give us a 1/2 here, okay? And so just by looking at this, I can kind of tell and say, yeah, there would be some value. It is not a nice, pretty value, but it will be a value. So it'll be safe to say that, hey, this y equals 1/2 constant would actually be wrapped up. We could say that it's wrapped up in the solution for the second part for that specific case of x. However, it really doesn't matter what what value of x we have. If y is 1/2, then of course it all goes to 0. It doesn't matter what x is. And of course, we showed that up here. Okay. And that's the main point I'm trying to get across here, that here it doesn't matter what x is. If y is 1/2, everything goes away. So even though we know that here we have a particular x value that would give us 1/2 on our own here, it doesn't really matter what x is, we'll still have it. So we still need to write it as a single separate solution here. So saying all that to say that our final answer here would be that we have y of x is equal to, and then of course this first piece would be 1/2 plus 3/2. Oops, slipped away from me there. So we got 3/2 e to the minus x squared, and this would be values of x between 0 and 1, excluding 1. Of course, the second piece would be e plus 3 divided by 2. And that would be e raised to the negative x squared. And that would be for values that are greater than 1. That will be that. And on top of that, y would be equal to 1/2 for all, or for every, that's what this symbol means, for all values of x within the real numbers, okay? So if we were looking at what our total solution is, then everything that I've written here is what our final answer actually is, okay? All right, so thank you all for hanging in with me with this video. I know it was kind of long, very long to be exact. Just know it was very long to record it too. But I wanted you to see, first of all, how this first order linear ODE thing works, the various ways that we could actually solve these types of equations, and the various things that you could possibly see. And so I did a lot of examples just to make sure that you saw as many different types of examples as I think you would probably see in the first year differential equation course. But I also wanted to make sure that I emphasized on finding intervals of interest and actually using these types of equations, in applications later on. So you got to know what kind of x values or t values or theta values you can actually plug into these differential equations once you actually solve for them. So I hope this video was helpful in getting some things straight about this particular concept. I look forward to seeing you in the next video. Take care.